Last week, we covered how to do free body diagrams for dynamics problems, okay? I hope you all managed to work through at least some of the problems on the tutorial sheets, okay? The solutions will shortly be on Blackboard. But today, we're going to take the next step. Last week, we did free body diagrams. Now we're going to apply what we learned last week and the equations of motion to try and work out the actual problems, okay? So this lecture is entitled Applying Newton's Laws, okay? The first thing we're going to do is we're going to, if this works, okay. So we'll divide it into two. We've got particle motion and rigid body motion. We'll look at the free body diagram, talk about the equations of motion and how we decompose those into component form. Okay, we'll do an example, and then we'll do another example on the visualizer that you can fill in the box. Okay, and then we'll do the same thing with rigid body motion. We'll do an example on the screen, and then we'll do another example using the visualizer. So it's quite a few examples today, but it's the best way to really illustrate what we're trying to achieve with these problems. Okay, so with particles, we learned last week that the equation of motion is basically Newton's second law. The sum of all the forces is the mass times the acceleration. Okay, that we all know, Newton's second law. And it states that the sum of all the forces acting on those, acting on our particle, is equal to the total mass m of the particle multiplied by the acceleration a of the particle. Okay. Now, as we remember, the first step that we needed to do when we were doing these free body diagrams was the coordinate system, okay? Now, there are two types of coordinate systems. We'll use the right-handed IJK coordinate system, but either of these are equally valid, okay? You don't need to worry too much about which one you use, but, you know, this is what we're generally going to be using, okay? Either X and Y or the IJK coordinate system. And the demonstrations that I'll do today and the examples will use the IJK coordinate system. Okay. Now in your exercises at the end of this section, there'll be times when you might want to use X and Y. Okay. And there are also times when you might need to use two sets of coordinate systems. If you've got two blocks, each block needs its own coordinate system, and sometimes those coordinate systems aren't necessarily aligned with each other. Okay. But you'll come across that in the problems. So, and once you've done your free body diagram, okay, you can then divide up the equations into their scalar component form, okay, and these sets of equations will be aligned along either the y-axis or the j-axis. And what we do is we then solve those separately, okay. What's going on? And so, in their component forms, Newton's second law looks like this. So we've got the sum of all the forces in the x direction, okay, equals the mass times the acceleration in the x direction. And obviously that's all multiplied by our unit vector I, because that's in the x direction. Okay, and then in the y direction, we have the same thing. The sum of all the forces in the y direction equals the mass times the acceleration in the y direction. Okay, and so this is our decomposed form of Newton's second law. And as said in the notes, you may see if we neglect I and j, we're working in x and y, then you may see the same equations, but without the I and j unit vectors, because we can assume that that's the situation. Okay, so this is the basis of what we're doing today. We had Newton's second law up there. The sum of all the forces equals mass times acceleration. We decompose those into the x and y directions, and we solve each of these separately to work out the accelerations. And then, if you wanted to, you can recombine them into a overall acceleration vector, which has a direction and a quantity and a magnitude. So we deal with these horizontal and vertical motions separately. Okay. So the best thing to do is perhaps look at an example. This is the example from last week. We had a crate that's resting on a surface, and there's a force P being applied to that crate at 30 degrees to the horizontal. Okay. And the crate's going to move to the right, and it doesn't tip over. So we're assuming this is our particle, okay? Now last week we went through how to do a free body diagram of this object, so I'm not going to do that again. But we should have had something that looks like that, okay? So we've got our coordinate system, we've isolated our object, we've applied all the external forces to that object, and that's equal to a kinetic diagram that indicates our direction of acceleration, okay? This is what we've assumed. And so we apply Newton's second law to this equation, to this diagram. We know that the sum of all the forces, so all the forces around the object, mg, p, n, and friction force, okay, are going to equal the mass times acceleration. And so you can do that, and you get the sum of all the forces. This is in vector form. We've not decomposed it yet. Equals mass times acceleration. Okay, so there's our ma. Equals p plus mg plus n plus ff. Okay, which are all the forces being applied to that particle. Okay, so that's the sum of all the forces equals mass times acceleration. That's Newton's second law in its essence. Now you'll notice that we've got our coordinate system ijk here, and all the forces ff, n, and mg are aligned along these axes. Okay, we've got mg in the j direction, n in the j direction, and the friction force in the in the I direction. Okay, but you notice that p is not along any of these axes. So what we need to do before we can do anything else is we need to decompose p into a component that runs along the I-axis and a component that runs along the j-axis, a vertical and horizontal component for p, okay? Because these equations, as I said, we can decompose them into x and y directions. But before we can apply that stuff, we need to work out what those components are of any force that's being applied that isn't along those axes, okay? In this case, the only force that's being applied is p, and we need to decompose p. So that's what we do next. We covered decomposition in the first lecture. Obviously, vector p can be decomposed into two scalars multiplied by those unit vectors, I and j. And we know from trigonometry that if the x direction, if we know the angle, which is 30 degrees, then it's just going to be the magnitude of p multiplied by the cosine of 30. That comes out to be 346.4 newtons. And then the y is magnitude of p times the sine of 30, okay, which is going to be 200 newtons. And so you can then place these numbers here in for px and py, and you end up getting the equation for the vector of p, but decomposed into x and y components, or I and j components. Okay? So that's what we do. We've decomposed p, so we've got px and py. And we can now move on to decomposing the Newton's second law equation. So we've got, in the x direction, we've got the sum of all the forces equals the mass times the acceleration in the x direction, and that's going to be px, okay, which is in the positive x direction, minus the friction force, okay? Now the friction, we've got a minus sign there because the friction force is acting in the opposite direction to positive x, okay, or positive I. So that's why, although in the vector thing, you add all the forces together because it's the sum of all the forces. These are vectors, okay? So obviously that's one vector and the opposite vector is in the other direction, but they're all still positive. But because we've decomposed it, we need to make sure that we've got our signs correct. So anything that's running in the same direction as x, okay, is positive, and anything that's in the opposite direction is negative, okay? So you've got ffx, minus ffx there, okay? In the y direction, again the same thing, the sum of all the forces is the mass times acceleration in the y direction. And we've got the vertical component of p, py. As we said, mg always acts downwards, okay, towards the centre of the Earth. So that's the minus mg. And then we've got the normal reaction force, ny, which acts in the positive direction. So we've got a plus there, okay. But you'll notice there's a few things about these equations. We don't know ax, we don't know the acceleration, okay, and we don't know the friction force. So there's two unknowns. And here we know what ay is because it's not moving in the vertical direction. We know that that's 0. We know what py is, but we don't know what ny is, okay. So we've got three unknowns. We've got a, the friction force, and the normal reaction force. But we've only got two equations. How do we go about solving this? Well, there is a third equation, and that third equation relates the friction force with the normal reaction force. And we saw this last week. The friction force is going to be the coefficient of friction, which is this character here, mu, multiplied by the normal reaction force. And so with this third equation, we've then got three equations and three unknowns. And so we can set about solving for the acceleration. And so the first thing to do is perhaps is to use this friction equation to work out what the friction force could be, okay? Or to work out what, and so to do that we need to work out what Ny is, okay? Well, since this equation in the y direction only has one unknown, and that's this Ny term, the normal reaction term, we first off solve in the vertical direction, okay? Now, as I said, we've got no acceleration in the vertical direction, so that we know that ma is going to be 0. So 0 equals all those terms, okay? And so we've got the vertical component of P minus the gravitational force, mg, okay, plus the normal reaction force. And so by rearranging this, we can solve for Ny, which is what we're looking for, okay? And we can plug in mg, obviously, is 50 times 9.81. We worked out the vertical component of P, which is 200, and so we can now work out that Ny comes out to be 290.5, okay? So that's the first step of our equation. So we've now got the normal reaction force, 290.5 newtons. So we now employ the friction force equation, mu times Ny, okay? So mu we said was 0.3, that was in the question. You'll generally be given the coefficient of friction. That's not something you have to assume. Okay, so we multiply that normal reaction force by the friction coefficient, and we get 87.15 newtons. So we now know what the friction force is. Okay, so we've now got two of the unknowns we've solved. We've got the normal reaction force and the friction force. Now we've got that, we can then go in to solve horizontally, because the horizontal equation had two unknowns. We didn't know what this was, okay, and we don't know what the acceleration is, and the acceleration is what we're trying to work out. And so here's our equation. We now know what the friction force is. Obviously this we can rearrange. You divide both sides by m, and you get the acceleration on its own. You plug in the numbers that we found. So we've got the horizontal component of p. We've got the friction force. Divide by 50, and you get the acceleration. So we can see that that crate accelerates at 5.19 meters per second to the right along the positive y-axis, okay, positive x-axis. So that's how we go about solving a particle problem, okay? There's quite a lot of maths, and it's all explained in your book. So if you go through the steps in your book, that's exactly what we've covered just here. So if it's sort of, you know, I can imagine sometimes when you're doing lots of maths in a lecture, you can sometimes glaze over, okay? But what we'll do is we'll go through an example now of a similar thing, and the example is on page 41. Now this is a particle example, so we don't need to worry too much about dimensions of anything, okay? And it says the mass of a VTOL aircraft, VTOL stands for vertical takeoff and landing, okay? It's 4,000 kilograms, okay? And its engines exert a force FF, and the force due to air resistance is FR, okay? So we've got two forces being applied to this object, okay, plus its mass, obviously. And we want to calculate the acceleration for these values of FF and FR, okay? So if we go to the visualizer. Okay, so here's the question. I'll zoom in a bit. Let's focus. Right, okay. So we've got first things we need to do is draw the free body diagram, okay? So the first step is a coordinate system. I should do the same coordinate system that we've used all over the place. Okay, we've got our IJK coordinate system. And we're assuming that this aircraft is a particle, okay? So I'm just going to draw it as a block. I don't need to worry about what shape the thing is. Okay, but I'm going to draw it as a block. Here's my block. There's the centre of mass. And applied to the centre of mass is obviously mg. I'll draw my forces in red. So that's going to be mg. Okay, and we've got these two forces, FF and FR, okay, which are applied, and these are in decomposed form already, okay. We've got I and J components to that, and we can see that this is going to be sort of in the positive I and positive j direction, so I'm just going to arbitrarily draw it like this, okay? We don't need to worry too much about its direction. FF, okay? And we've got a resistance force, which is minus 1000 I, so it's in the minus I and j directions, okay? And so I shall draw that in this direction. FR, okay, and we know that that's going to equal our kinetic diagram, which looks similar size, similar block, okay? I don't know which direction it's going to move, but I'm going to assume that it's somewhere like this. It doesn't really matter, we'll find out in the end. We're going to have an acceleration in some direction, okay? That's what I'm assuming. Obviously, we've got these in decomposed form, and we'll find out what the acceleration is in decomposed form, okay? So it should be relatively simple. And so that's our first step. There's our free body diagram. The next step is to apply the equations of motion. And we know that the equations of motion is the sum of all the forces. It's going to be the mass times its acceleration. Okay, this is in vector form. And we just add up all the forces. Well, there's three forces. We've got mg plus ff plus fr. Okay? Newton's second law, the sum of all the forces equals mass times acceleration. So the next step, once we've got this equation, we then have to decompose it into the x and y coordinates, okay? And so the next step, we'll decompose this into x. So if I write the x direction here, we've got m times ax, okay? This is obviously in the I direction, so I'll write I, equals, and then we have to look at all the forces that are being applied in the x direction. Obviously we've got a positive component of ff, okay, so that's up here, there's our x direction, so we've got f in the x direction times by I, plus, well, we've got a force in the component of the resistance force in the x direction. So I've got plus Fr x times by I, okay? And obviously there's no horizontal component of the mass force, so that's our equation. And so what we can do is we can then rearrange this. If we divide both sides by m, we have ax in the I direction equals, then we're going to have ff in the x direction plus fr in the x direction divided by m times by the unit vector. And so we can then say that ax I equals, and then we plug in the numbers. Well, we know that the horizontal component of the thrust force is 11,000. Okay? And we know that the horizontal component of the resistance force is minus 1,000. Divide by 4,000. And that comes out to be 2.5 I, don't forget your vectors, meters per second squared. So there's the horizontal component of the acceleration. So we know that if we've got our ma there, okay, in the kinetic diagram, we know it's going to be in some direction, arbitrary direction. But we know that the horizontal component of that vector is going to be 2.5 meters per second squared, okay? So that's the horizontal bit, and we do exactly the same thing for the vertical bit, okay? In the y direction, okay, we've got mass times acceleration in the j direction, okay? And again, we've got all our forces. Now, if you look at the free body diagram, we've got a vertical component of ff, we've got a vertical component of fr, and we've also got, obviously in this case, gravity, okay? So I do the same thing again. We have F Fy times by j plus Fry times by j plus mg, okay? No, yeah. That's going to be obviously minus times by j, because it's always downwards, okay? Excuse the mistake. And so we can rearrange that, again, solving for the acceleration, ay times by j. We've got Fy plus Fry minus mg divided by m, unit vector. And so we'll plug in the numbers again. Ay, j equals. Now if you notice, the vertical component of the thrust force is 51,000 and the vertical component of the resistance force is minus 1,000. Okay, so we do the same thing again. 51,000 minus 1,000 minus mg, well that we know that's 4,000 times by 9.81, all divided by the mass, 4,000 j, and that comes out to be 2.69 j meters per second squared. Okay, so there's the vertical component of the acceleration. And so we can write the vector A, okay, is going to be obviously AXI plus AYJ, okay, the decomposed form. We plug the numbers in, and we end up with that coming out to be 2.5 I plus 2.69 J meters per second squared. And there's your solution. Okay, are there any questions on this problem that we've just done? Good, that's the way I like to see it. Okay. Has everybody got it down yet? No? Leave it up? Okay. Okay. Right. Okay, so that was the example with a particle. Okay. Now, for rigid bodies, okay, we know that with rigid bodies, it has a mass, okay, but it's also got a size and a shape, okay, so it's a bit more complicated with rigid bodies, but we can do more complicated things. Now, because rigid bodies have a mass and a size and a shape, okay, there are two equations of motion. We've got Newton's second law, F equals ma. We've also got the rotational version of Newton's second law, which is the sum of all the moments equals the moment of inertia I times by alpha, which is the angular acceleration, okay? And so these are our two equations of motions. Okay, they're both Newton's second law. One is to do with linear motion, and one is to do with rotational motion. And so we can do the second example, okay? Again, this is what we saw last week. We have a crate resting on a surface, okay, and there's going to be moment applied to that crate, a force applied to that crate P, okay, and obviously because it's a rigid body, there are dimensions associated with the crate. Okay, we've got the dimensions of the size of the crate, and we've got the dimensions of where that force P is being applied. We can assume that this is a homogeneous quantity, so we know that the centre of mass is in the centre of there, okay. And so we did this last week. We've got our free body diagram and our kinetic diagram of that crate. So here's our coordinate system. There's the isolated object. Here are all the forces being applied on it, okay. We've got P, mg, the friction force, N, okay, and we've also got our dimensions, which is what you also need when you're doing a rigid body. And that's going to equal the acceleration of the crate, okay? And so, in this case, all the forces lie along the I and J axes. So we don't need to decompose any forces. We just take the x and y components of those forces, and obviously, some of them will have no y component, and some of them will have no x component, okay? And so we apply, the last thing is we're going to make the assumption that the crate slides, okay? We're going to assume it doesn't topple. So we're making the assumption that this force N, this reaction force, okay, is counteracting P, so that the moment being applied by P around the centre of gravity is being counteracted by the force N, which is in the opposite direction around that centre of gravity. That's why we've got N doesn't necessarily pass through the mass centre. If you've got an object, here's an object, okay, and it's sliding along the table, okay, if I'm applying a force at the top of the object here, okay, obviously, if it doesn't slide, that's going to cause it to rotate, yeah? If around the centre of mass, okay? If I apply a force at the top, okay? Now, obviously, to counteract that, we're making the assumption that the crate doesn't slide. There must be a force at the bottom that goes around the centre axis that's going to try and rotate it the other way, okay? That's why if you apply it at the centre of mass, obviously it's not rotating. If you apply this side, it's going to help it rotate as well. So it needs to. That's why N isn't passing through the centre of mass, okay? You've got to have two things, because we're making the assumption that it doesn't rotate, and so N must counteract P. Well, that's the assumption that we're making. And so the next step is to start coming up with our equations. We apply the equations of motions. Well, this is the linear version of Newton's second law. The sum of all the forces is the mass times acceleration, and here are all our forces. We've got P, gravity, the normal force, and the friction force. Okay? And then, so this is the x component. We've got all the force in the x direction. It's mass times acceleration. And we've got the horizontal, P, and we've got the horizontal, the friction force, okay? Friction force, don't forget, friction force always opposes motion, okay? You never get a friction force that's going to increase motion. It always opposes motion. And so substituting in for the friction force, we've got obviously mu times the normal reaction force, okay? And then obviously in the y direction, we've got the same thing. This is obviously 0, it's not moving in the y direction, so we don't need to worry about its acceleration. We've got gravity and the normal reaction force. So looking just at the vertical direction, as I said, AY is 0, so you can go and solve for the normal reaction force. That's just going to be mg, 490.5. And so the acceleration of the block, okay, so we're looking at just the linear stuff that's going on. The acceleration of the block, we applied the version in the x direction, okay. We now know what ny was. We found that in the last slide, okay. Px, we know, it's just 600 newtons in the positive I direction. So you divide all that by the mass, and you get the acceleration of 10 meters per second squared in the I direction. So that's relatively straightforward. There's nothing too complicated in that. You decompose the problem into the x and y coordinates, and you apply the equations of motion, and you have your solution. But we made an assumption that the crate does not tip, okay? The crate doesn't topple over. And so to check this, if we go back to the example, I think it's this slide. So we're making the assumption that this doesn't tip, okay? Now there's this dimension here, x, okay, x. That's the distance here. Now, we can work out what x is by looking at the moment equation. And if x is greater than 0.5, if it's out here, then we realise that we made the wrong assumption. The crate does topple. Okay, but if x is between 0 and 0.5, then we made the correct assumption. The crate does not topple. Okay? And so by looking at the equation, if x comes between these two values, 0 and 0.5, then this assumption is correct. Now in your notes there's a small mistake, okay? Page 43, between slides 22 and 23 there's a block of text, okay? So near the bottom. And I've said we should calculate x, and if this is within the range of 0 is less than x, which is less than or equal to 5 meters per second. Obviously, we're looking at 0.5 meters per second, not 5 meters. 0.5 meters, not 5. Okay, small mistake. So this is correct, what's on the screen. Then this assumption is correct. Oops. And so, to determine x, we should use the moment equation, which we had initially. The sum of all the moments equals I times alpha. Okay, in terms of signs, we need to think of a convention. And the convention that I'm using in this example is that all the moments in the clockwise direction are positive, all the moments in the anti-clockwise direction are negative. And for a non-tipping crate, we're assuming that the crate doesn't tip, so alpha, the angular acceleration, is going to be 0. Okay? And so we apply our moment equation. We've got the sum of all the moments equals I times alpha. Okay, well that's going to be 0 at the end there. And we've got all the forces multiplied by their distance from the centre of mass, because we're taking moments around the centre of mass. Okay? Which is why we're using Ig. And so we've got the force being applied, P, okay? And that's 0.3 meters away from the centre of mass in the direction that's being applied. We've got the friction force, which is at the boss rate, so that's half a meter away from the centre of mass. And then we've got this normal reaction force, which we don't know where it's being applied. That's our dimension x that we're trying to find. Now we know px, we know the friction force, we calculated them in the previous steps. Ny we also know, so that we've got one equation, one unknown, which is x. And so we go through the motions of solving for x. We put nyx on one side, okay? Everything else on the other. We divide by ny, which leaves us with x on its own. You apply the sums, do the calculations, and x comes out to be 0.467 meters, which is nicely between 0 and 0.5. So we were right to assume that the crate doesn't tip. That's less than 0.5 meters. We were correct. The crate doesn't tip. So now we know everything about the motion of that crate. We know that it doesn't tip. We know that it accelerates in the x direction at 10 meters per second. And we know that it's not going to topple over. Okay? Now I've got one more example that we'll do again on the screen. Now the example is a common occurrence. You go to the supermarket, you bought some wine or whatever, okay? You place the wine on the conveyor belt for the supermarket. Does the bottle of wine topple over or not? Should you lay it down on its side, okay? Well, here we've got a bottle, the supermarket conveyor belt. It's got a mass of 1 kilogram, okay? And the radius of the bottom of the bottle is 5 centimeters, okay? So the diameter of it is obviously 10, okay? And if we're making the assumption that the belt has an acceleration of 1 meters per second squared, okay? So the moment the person picks up the last item on the conveyor belt, starts moving, we're assuming that it accelerates at 1 meters per second squared, okay? Does the bottle topple when the belt is turned on? We don't know. But we can work it out by using dynamics. There was a bit of information that I forgot to write in the question, and that's the height of the centre of mass is 20 centimeters. So, the first thing to do is draw the free body diagram. Again, We use the standard set of coordinates, I, J, and K. I'll draw my bottle. Here's my bottle. We've got our centre of mass here. I'll draw the dimensions in green so they're clear. Obviously there's going to be a force of the mass. That's mg. We've got a normal reaction force. That's 0.2. 20 centimetres, yeah. We've got our normal reaction force, okay, which we're positioning at this point here. And we've got a force being applied by the belt in this direction, FB. We're assuming that there's, because it's not sliding along the belt, we're assuming that we don't need to worry about friction, okay? The belt and the bottle are the same thing, okay? Now you'll notice that things aren't correctly lined up. We've got a few dimensions here. We've got this dimension here, which is x, okay? We don't know what that is. And we've got our height of the centre of mass, 0.2, okay? And notice I've positioned n so that, if the bottle's going to topple, then x will be greater than the radius of the bottle, okay? And that's going to equal our kinetic diagram. So I'll draw the same thing again. Bottle, centre of mass, mass times acceleration. Okay, so it's again a relatively simple problem, okay? Make sure you draw the good free body diagram. It'll help. And so we do the sum of all the forces. The same thing again. Equals mass times acceleration. So we've got mg plus fb, the force of the belt, plus n. Okay, well in the x direction, do the same thing again, max. I'm not going to bother with the ij's and k's. We've got f, b, x, okay? They're the only forces that are acting in the x direction, is the force of the belt, okay? Now we know the acceleration, we've been given that, that's 1 meters per second, okay? We know the mass of the bottle, that's 1 kilogram, and so that's going to be 1 times 1. And so FBX equals 1 Newton. Okay? In the y direction, again, I'm not using I, J, and K, I'll just say in the y direction, we've got minus mg plus n. Okay? Well, we know that it's not accelerating in the y direction, okay? It's not taking off from the belt or sinking into the belt, so we know that that's going to be 0, okay? And so we can say that n equals mg, which is going to be 1 kilogram times by 9.81 meters per second, so that's going to be 9.81 newtons. Okay, so that's n. So we now know what n and the force of the belt are. Okay, we've got 1 Newton for the force of the belt and the normal reaction force, 9.81. So now we can apply the sum of moments, okay, moments. So we said the sum of all the moments, okay, in the clockwise direction equals I times around the centre of gravity times by alpha, which we know is 0, because we're assuming that it's not going to rotate. And so the force is being applied, mg is being applied at the centre of gravity, so there's no moment attached to that. But we've got a force clockwise direction from n, so that's going to be n times by x. And then we've got a force in the negative direction, which is our force of the belt, minus Fb times by the height, which is 0.2. There, that's a G. Capital G. And so the moments, you see we've got x times n, okay? Because if you move n up to next to where the centre of mass is, obviously that's going to be the distance x away. And the same with the force of the belt. That's going to be 0.2 meters, okay? Because you're applying moments. Moments is force times the distance, okay? So we've got 0 equals n, x minus Fb times 0.2. And so we know that nx equals Fb times by 0.2. And so x we know is going to be Fb times by 0.2 divided by n. Well, we know Fb, that's 1 times by 0.2 divided by 9.81. And that comes out to be about 0.02 meters. Now we know the radius of the bottle. The radius of the bottle is 0.5. And so, because 0.02 is less than 0.05, okay, we know that the bottle does not tip. Okay? So we know that it's safe to place the bottle upright on the conveyor belt. Now don't make that assumption, because I don't know how fast a conveyor belt accelerates, but I've taken it to be 1 meters per second squared. It might not be. So, has everybody got that down? Are there any questions on this? That's a clockwise circle. Because we're making the assumption that clockwise is positive, okay? Anti-clockwise will be negative. Am I okay to switch to the PC? Okay, I'll just do a quick summary. Okay, so the summary, remember to decompose the equations into the x and y coordinates, okay? If you're dealing with linear translational motion. Make sure that your signs make sense with your coordinate system. It really helps if you draw a free body diagram. Even if the question doesn't ask for it, if you draw a free body diagram, you can guarantee that your signs will make sense, okay? You know what's positive and you know what's negative, okay? Draw the free body diagram. Friction always opposes motion, okay? It never helps it along. Whenever you're doing moments, always make sure you've established which direction is positive. The assumption that clockwise is positive. That will not make sense for you. If you want to make anti-clockwise positive, say so, that's fine, but be consistent, okay? And lastly, if you're asked to find velocities and position, okay, just use the standard constant acceleration equations. We'll deal with varying acceleration next week, okay? But the standard constant acceleration equations, which you did in physics, they're also in your revision notes, okay? You can apply them and you'll get things like, because you'll get, in the examples, there'll be questions like, find the velocity after 3 seconds. Okay, so that's it. If you've still got a form to fill in or hand back, I can take it now. If you want to hand it back next week, that's fine too. Okay. Thank you.
Those ones weren't used. Those ones were answered.
Thank you.